Hi all, today we are going to study about medium transmission lines. Medium transmission lines are those which are having length about 50 to 150 kilometers and their voltage ratings greater than that of 20 kilovolt. In medium transmission lines, the effect of line capacitance cannot be neglected, just like how we have done in the case of short transmission lines. For analysis purpose, we will consider that the capacitance of the transmission line is concentrated, and they are considered as capacitors shunted across the transmission line at one or more points. Generally, three methods are used for the analysis of medium transmission lines. They are N-condenser method, Nominal T method, and Nominal Pi method. You have to study these two methods in detail, that is Nominal T method and Nominal Pi method. We will begin with the Nominal T method. In this method, the line capacitance is assumed to be concentrated at the middle of the transmission line, and half of the transmission line resistance and transmission line reactance are assumed to be concentrated at either sides of this capacitor, as you can see in this figure. This is actually the Nominal T method. In this equivalent circuit, VR represents the receiving end voltage, sending end voltage is Vs, Is represents the sending end current, and IR is indicating the receiving end current. The current which is flowing through this shunt capacitor is IC, and the voltage which is appearing across them is represented as V1. For analysis purpose, we will be using the basics, Kirchhoff's current law and Kirchhoff's voltage law. If you consider this node, we will be able to write the relation for this sending end current as the sum of receiving end current and the current which is flowing through this capacitor. By applying the Kirchhoff's voltage law, we will be able to write the relation for V1 as the sum of VR and the drop which is occurring in this impedance branch. Similarly, while applying KVL in this loop, we will be able to write the relation for Vs as the sum of V1 and the drop which is appearing across this impedance branch. V1 can be written as the product of this capacitive current and capacitive reactance. The capacitive reactance is usually indicated as Xc, which is equal to the relation 1 by j omega c. For analysis purpose, we will consider an inductive load here, as 90% of the loads in the universe are inductive in nature. So definitely the current which is flowing through this load will be lagging the voltage which is appearing across the load by some angle, as you will be able to see in this vector diagram. VR is taken as the reference vector, and this current IR is lagging VR by angle phi r. In order to obtain the value of Vs from this VR and IR, first you have to obtain the relation for V1 by using KVL in this loop, and then we can easily obtain the value of Vs by applying KVL in this loop. Just like we have mentioned now, the value of V1 can be determined by applying KVL in this loop. So by applying KVL in this loop, we will be able to obtain V1 as the sum of VR and the drop which is occurring in this impedance branch. So with VR, we have to add the drop which is occurring in the impedance branch to get the value of V1. That is, along with VR, I have to add the vector IR into R by 2 and IR into XL by 2. So in order to draw the vector IR into R by 2, we have to draw a line parallel to IR at the tip of VR. Definitely, the length of this IR into R by 2 will be less than that of IR, as the value of R is quite small. Now to draw the vector line of IR into XL by 2, we have to draw a line perpendicular to that of IR into R by 2. So this indicates the IR XL by 2 line. So now VR plus IR into R by 2 plus IR into XL by 2 will be giving you the value of V1. The resultant of IR into R by 2 and IR into XL by 2 will be giving you the value of IR into Z by 2. This is actually the impedance triangle. So directly we can write VR plus IR into Z by 2 will be giving you the value of V1. When I say VR plus IR into Z by 2, it's not actually the arithmetic sum, it's actually the vector sum of VR and IR into Z by 2. That will be giving you the value of vector V1. To find the value of Vs, we have to apply Kirchhoff's voltage law in this particular loop. So while applying Kirchhoff's voltage law in this particular loop, we will be able to obtain Vs as the sum of V1 and vector Is into R by 2 and vector Is into XL by 2. So along with vector V1, we have to add is into r by 2 and is into xl by 2 to get the vector vs. In order to draw this vectors is into r by 2 and is into xl by 2, we first need to fetch the vector is. From the equivalent circuit diagram, it's clear that is is actually the sum of vectors ir and ic. So first we need to draw ic vector. From this equivalent circuit, it's very clear that the current which will be flowing through this capacitor will be leading the voltage across it by 90 degrees. So you can draw this vector IC perpendicular to that of the voltage vector V1. So while drawing this vector at the tip of this IR and taking the sum of these two vectors IR and IC will be giving you the value of IS. That is, to get the vector IS, you have to first draw a line at the tip of IR perpendicular to that of vector V1. That will be indicating the vector IC, and the vector sum of these two vectors will be giving you the value IS. After getting this IS vector, this IS into R by 2 vector can be drawn by drawing a line parallel to that of this IS vector, and IS into XL by 2 can be drawn by drawing a line perpendicular to that of IS into R by 2. So this V1 plus IS into R by 2 plus IS into XL by 2 will be giving you the value of vector Vs. And from this impedance triangle, we can say that this resultant of Is into R by 2 and Is into XL by 2 vector will be giving you Is into Z by 2. Now we will write all the associated relations from this vector diagram. As vector Vr is taken as the reference one, we can write it as Vr angle 0, that is Vr plus J0. Vector IR is lagging vector Vr by phi r degrees. Therefore, this IR can be written as Vr angle minus phi r. In rectangular form, they can be written as IR into cos phi r minus J sin phi r. As we have mentioned before, V1 is actually the sum of Vr vector and IR into Z by 2 vector. That is shown here, Vr plus IR into Z by 2. We will make the substitution of IR and Z by 2 from the previous slide. We can write IR as IR into cos phi r minus J sin phi r in rectangular form. Z by 2 can be written as R by 2 plus J into XL by 2. Vector IC is obtained by dividing vector V with the capacitive reactance. Capacitive reactance is actually 1 by J omega C. Therefore, vector IC can be written as J omega C into vector V1. Instead of omega, we can make the substitution 2 pi f here. By using KCL, we have written that IS is equal to IR plus IC. And it was clearly seen in the vector diagram that vector Vs is actually the sum of vector V1 and Is into Z by 2. You can make the substitution of vector V1 from here and vector Is from here. Then you will be able to get the value of vector Vs in terms of Vr and IR. You may write down that relation by yourself. Next, we are going to see a numerical problem associated with the nominal T method of medium transmission line. Whenever such problems are asked, let it be in the case of short transmission line, medium transmission or long transmission lines, the very first thing you have to draw is its equivalent diagram, and then you must draw its vector diagram also. You don't need to by heart this vector diagram and equivalent circuit. You just need to understand it. If you know how to draw the equivalent circuit, then definitely you will be able to obtain the vector diagram from the equivalent circuit itself. Now let's see this problem. It's a 3-phase overhead transmission line and its length is 100 km. So it's clear that it's a medium transmission line. Resistance per kilometer per phase is given as 0.1 ohm. See, please note here it's actually resistance per kilometer per phase, per kilometer. Inductive reactance per kilometer per phase is given as 0.2 ohm. Capacitive susceptance, it's not capacitive reactance which is given here, it is capacitive susceptance. Capacitive susceptance is actually the inverse of capacitive reactance. You are asked to find the sending end current, the value of Is, sending end voltage, value of Vs, sending end power factor, that is the cosine of the angle between Vs and Is, transmission efficiency, that is the output power at the load side divided by the sending end power. When supplying a balanced load of 10,000 kilowatt at 66 kV and power factor is 0.8 lagging. These are actually the load parameters. It's clearly mentioned that you have to use nominal T method to solve this problem. So just like as I mentioned now, you have to first draw the equivalent circuit followed by its vector diagram. Even though the overhead transmission line given in this problem is a three-phase system, we always work in phase rather than line-to-line values. That can be very clearly seen from this equivalent circuit. So in this question, this value of three-phase voltage given is actually line-to-line voltage. Since there is no specific mention about the three-phase connections, that is whether it is star connected or delta connected, by default we can consider it as a star connection. So this value of 66 kV is actually line-to-line voltage in the case of star connection. But the voltage which you require here is actually phase voltage. So in order to obtain the phase voltage, you have to divide this voltage by √3. That is being shown here. Receiving end voltage per phase is obtained by dividing it with √3. From the relation of three-phase power, that is √3 VL IL cos phi, we will be able to obtain the value of IR because the value of power, line voltage and the power factor is given. So √3 VL IL cos phi will help you to find the value of receiving end current. As the values of resistance and reactance per kilometer is given, we will be able to find the value of complete resistance by dividing it with the total distance of the transmission line, that is 100 km. So this will be giving you the value of total resistance per phase and total reactance per phase. So the total impedance can be written as 10 plus j20. For calculations to be more simpler, we will be doing the analysis in complex notation form. Therefore, vector VR can be written as 38,105 volt, angle 0. Vector IR is written as IR angle minus phi r. In rectangular form, we can write it as IR cos phi r minus j sin phi r. As we have mentioned before, V1 is actually the sum of vector VR and IR into Z by 2. Make the suitable substitutions, you will be able to obtain the value of V1 as 39,195 plus j into 545. Next, we have to determine the value of charging current IC. IC is actually obtained by using the relation J into omega C into V1, but the value of omega C is given directly in the problem as capacitive susceptance. So you have to substitute that value here, then you will be able to get the value of charging current. From the receiving end current vector and charging current vector, we will be able to find the value of sending end current by adding these two values. So we will be able to get the value of sending end current as 87 minus j into 49.8 in rectangular form. By converting it into polar form, we will be able to get it as 100 angle minus 29 degrees. In this 100 will be indicating the magnitude of sending end current. Next, it is asked to find the value of sending end voltage. Sending end voltage can be determined by adding vector V1 and vector IS into Z by 2. Make suitable substitutions and you will be able to get the value of Vs as 40,145 angle 1 degree. This value is actually per phase sending end voltage, but in the problem, when it is asked to find the sending end voltage, you have to calculate the value of line value of sending end voltage. So in order to obtain the line value of sending end voltage from the per phase value of sending end voltage, you have to multiply it with √3 and you will be finally able to get the value of sending end voltage as 69.533 kilovolt. From this polar form of vector Vs, we very well know that this angle 1 degree 40 minutes is actually the angle this vector is making with vector Vr. Similarly, from the polar form of vector Is, we will be able to know that minus 29 degrees 47 minutes is actually the angle this vector Is is making with vector Vr, as vector Vr is considered as the reference vector. It's very clear that this vector Is is lagging the vector Vr by 29 degrees 47 minutes and vector Vs is leading the vector Vr by 1 degree 40 minutes. So whenever we are drawing this vector diagram, if we are considering this vector Vr as the reference one, as this vector Vs is leading the vector Vr, you have to draw it in anti-clockwise to vector Vr. See, vector Vs is drawn in anti-clockwise to vector Vr. Similarly, since this vector Is is lagging vector Vr by 29 degrees and 47 minutes, you have to draw this vector Is lagging vector Vr. In order to draw this vector Is, you have to draw it in clockwise to vector Vr. As you are asked to find the sending end power factor, you have to find the angle between Vs and Is, and then you have to take the cosine of the angle between this Vs and Is. The angle between this Vs and Is is actually the sum of this theta 1 and theta 2. The values of theta 1 is 1 degree 40 minutes and the value of theta 2 is minus 29 degree 47 minute. That is, this angle is 29 degree 47 minutes and this angle is 1 degree 40 minutes. So adding these two angles, we will be able to obtain the value of angle between Vs and Is, which is actually phi s. Taking cosine of that angle, we will be able to get the sending end power factor value. Next, we are asked to find the we are asked to find the transmission efficiency. So in order to find the transmission efficiency, we have to find the value of sending end power. Sending end power is determined by using the relation 3 V phase I phase cos phi s. We have determined the value of Vs, Is. This is actually the phase values of sending end voltage and sending end current. You make the substitutions here, you will be able to get the value of sending end power as 10273 kilowatt. In the question, it's directly given that the power at the receiving end is 10,000 kilowatt. We have calculated the sending end power and the receiving end power is directly given in the problem. So we can easily determine the value of transmission efficiency by dividing the receiving end power with the sending end power and multiplying it with 100, and we will be obtaining it as 97.34%. You don't need to by heart all these relations to solve the problem. You just need to know this equivalent circuit and this vector diagram. From there you will be able to write the relation by yourself. And once after writing the relations by yourself, you can make the suitable substitutions and easily find the final answers. Please be very careful with the line voltage values and the phase voltage values. Next, we are going to see the nominal pi method of medium transmission line. In this method, the transmission line capacitance is assumed to be divided into two halves, and each half is said to be concentrated at both ends of the transmission line. See here, this capacitor is having a value C by 2 and this capacitor is having a value C by 2, and this capacitor is placed at the receiving end and this capacitor is placed at the sending end. By analyzing this equivalent circuit and by applying KCL at this node, we will be able to obtain the vector IL as the sum of vectors IR and IC1. Similarly, we will be able to obtain vector IS as the sum of vector IL and IC2. By applying KVL in this loop, we can find vector Vs as the sum of vector Vr and the impedance drop vector. Now let's draw the vector diagram of this nominal pi method. Just like in the case of short transmission line and nominal T method, we will consider this vector Vr as the reference vector, and the load is assumed to be an inductive in nature. Therefore, this current IR will be drawn lagging vector Vr by phi r degrees. The current vector IC1 will be leading the voltage which is appearing across this capacitor by 90 degrees. Similarly, the current vector IC2 will be leading the voltage appearing across this capacitor by 90 degrees. As we very well know that this capacitor is connected in parallel with the load, therefore the voltage which will be appearing across this capacitor will be the receiving end voltage. As this capacitor is connected in parallel with the input, the voltage which will be appearing across this capacitor will be the sending end voltage. So in order to draw the vector IC1, we have to draw a line perpendicular to that of vector Vr. So at the tip of vector IR, we will be drawing a line perpendicular to that of Vr, that is vector IC1. From the equivalent circuit, it's clear that vector IL is obtained by adding vector IR and IC1. So this resultant of this vector IR and IC1 will be giving you the value of line current IL. Similarly, from the equivalent circuit, vector IS can be drawn by adding the vectors vector IL and vector IC2. Vector IC2 can be obtained by drawing a line perpendicular to that of vector Vs. So first we have to obtain the vector Vs. Vector Vs is obtained by applying KVL in this particular loop. By applying KVL in this particular loop, we will be able to obtain vector Vs as the sum of vector Vr and the impedance drop which is occurring in this transmission line. So along with vector Vr, we have to add IL into R vector and IL into XL vector to obtain the vector Vs. Only after obtaining the vector Vs, we will be able to draw the vector IC2 perpendicular to vector Vs. So first we have to draw this vector Vs before drawing vector IC2. So in order to obtain vector Vs, we will be using the KVL rule. So along with vector Vr, we will be adding vector IL into R. Vector IL into R is drawn by drawing a line at the tip of vector ER parallel to vector IL. Similarly, vector IL into XL is obtained by drawing a line perpendicular to vector IL into R. While drawing also, you must ensure that you are drawing this line parallel with vector IL and you are drawing this line perpendicular to this line ILR. And if you draw a line joining this points A and C, that will be giving you the value of IL into Z, or that will be giving you the vector IL into Z. And this triangle ABC will be indicating the impedance triangle. So now adding this vector VR, IL into R, IL into XL, we will be able to obtain the vector Vs. Once after Vs is obtained, you have to draw a line perpendicular to Vs at the tip of IL. That will be indicating the vector IC2. And if you are adding these two vectors, you will be able to get the vector IS, and the angle between this Vs and IS will be giving you the value of phi s. The charging current at the receiving end can be obtained by dividing the voltage with the capacitive reactance. The capacitive reactance over here is 1 by j omega c by 2. So VR divided by 1 by j omega c by 2 will be giving you the value VR into j omega c by 2. Instead of omega, we can make the substitution 2 pi f. So this 2 and this 2 will get cancelled. Now IL can be written as the sum of vector IR and IC1. Either from this vector diagram we can write, or we can write it from the equivalent circuit also. Similarly, Vs can be written as the sum of vector VR and vector IL into Z. IL into Z is not shown here. Whenever you are drawing the vector diagram, you must mark that also as a dotted line. Instead of Z, we can make the substitution R plus J into XL. Similarly, IC2 can be obtained by dividing Vs with the capacitive reactance. So this IC2 can be written as Vs into j omega c by 2. Is can be obtained by adding the vectors IL and IC2. Next, we are going to see a numerical problem associated with the nominal pi method. Just like I mentioned before, whenever such sort of problems are asked, you must keep in your mind that the equivalent circuit and vector diagram must be drawn first. Some marks are specifically there for drawing the vector diagram and the equivalent circuit. Now let's see this problem. In this problem, it's actually a three-phase transmission line and its total length is 150 kilometer. Resistance, inductance and capacitive shunt admittance values are given. All these values are given in per kilometer. So in order to find the value of total resistance, total reactance and the total shunt admittance value, you have to multiply it with the total length. It is delivering a load of 50 kilowatt at the receiving end, and the voltage which will be available at the receiving end is, that is line to line voltage available at the receiving end is 110 kV, and the load being supplied at 0.8 power factor lagging. That is the angle between VR and IR can be easily find out by taking the cosine inverse of this 0.8. Specifically, you are asked to use nominal pi method, and you have to determine the value of sending end voltage and sending end current. So after drawing this vector diagram and equivalent circuit, vector diagram is not shown in the problem, but you have to draw, you must draw the vector diagram also. Then you have to follow the same steps as we have followed in the previous problem of nominal T method. First we have to find the value of VR. The receiving end power value is given and the receiving end voltage value is given as 110 kV. That is actually the line to line voltage. Therefore the first we will find the phase voltage by dividing it with root 3. By default we have to consider the three-phase system as a star connection one. Then in such a star connection system, the three-phase power is given by root 3 VL IL cos phi. So from there we will be able to determine the value of line current. In the case of star connection, the line current is same as that of the phase current. Therefore this will be giving you the value of phase current itself. Then by using the complex notation form, we can write VR as VR angle 0. IR can be written as IR angle minus phi R. In rectangular form, we can write it like this. ISC1 is obtained by taking the product of VR and J into Y by 2. The value of Y is given directly in the problem. That is, shunt admittance is given directly in the problem. But that is for per kilometer. So in order to get it for the complete 150 kilometer, you have to multiply it with 150. So making the suitable substitutions, we will be able to determine the value of IC1. From the equivalent circuit, it's clear that IL can be obtained by adding the vectors IC1 and IR. Vector IR and IC1 is known now. So add these two vectors to calculate the value of vector IL. And next we will be finding the vector Vs by adding vector VL and vector IL into Z. Make suitable substitutions because all these parameters has been already determined here. Then we will be able to get the value of Vs in polar form as 82.881 angle 11 degrees 47 minutes. So in this Vs vector value, this indicates the magnitude of vector Vs, and this is actually the angle by which this vector Vs will be leading the vector VR. Since the value we are obtaining here is per phase value, in order to determine the line voltage value, you have to multiply it with root 3, and thus we have obtained the sending end voltage. Next we have to determine the value of sending end current. For obtaining the value of sending end current, you have to add vector IL and vector IC2. So first you have to find the value of vector IC2. IC2 can be easily find out by using the relation J vector Vs into I by 2. Make suitable substitutions. Thereafter add vector IC2 and vector IL to get the vector IS. And the magnitude of this vector IS is 306.4. Here you don't have to multiply it with root 3 because in the case of three-phase star system, line current is same as that of the phase current. So this phase current will be same as that of the sending end line current value. This problem you have to do it by yourself. A 100 kilometer long three-phase 50 Hz transmission line has following constants. All the parameters are given. And it is applying a load at the receiving end. The load parameters are given. It's not 0.8 power factor, it's 0.9 power factor lagging. And the receiving end line to line voltage is 66 kilovolt. You have to calculate by using nominal pi method sending end power factor. Sending end power factor can be determined after obtaining the values of vector Vs and vector Is. The polar form of vector Vs, from the polar form of vector Vs you will be able to find the angle which vector Vs is making with vector VR. Similarly, from the polar form of vector Is you will be able to obtain the angle vector Is is making with vector VR. And then from there you will be able to find the value of phi s, and taking cosine of that angle will be giving you the sending end power factor. Once after determining the value of Vs and VR, you can easily find the value of regulation by using the relation Vs minus VR divided by VR into 100. Next you are asked to find the value of transmission efficiency. Receiving end power is given directly in the problem. You have to find the value of sending end power. Thereafter dividing receiving end power with sending end power, you will be able to get the value of transmission efficiency. Sending end power can be determined by using the relation Vs Is cos phi s. That is in the case of a single phase system. Here we are dealing with a three-phase system. Therefore, the sending end power can be determined by using the standard relation 3 into Vs Is cos phi s, where Vs and Is is indicating the phase values. Do this problem by yourself and send me the answers. With that, we are completing the topic medium transmission lines. In the next class, we will begin with long transmission lines. Thank you.